In this lesson we'll look at the properties of what are known as surds. Now, what is a surd? Well, a surd essentially is the square root of an integer which ends up being an irrational number. Now, for example, the square root of 2. If you were to enter that into your calculator, you should get something like this. Now, if you look at that number, that's not the full story. This number, if you had room on your calculator screen, would continue on indefinitely. What it's called a non-repeating, non-recurring decimal. So there's no pattern emerging in these numbers. They just continue on in a sequence of numbers to infinity. As a counterexample, consider the square root of 4. Now that's not a surd, because we know that the square root of 4 is 2. It's not non-repeating and non-recurring in decimal format, it's simply 2. So this sort of number here falls into the family of what are known as irrational numbers. A surd then is a square root that ends up being an irrational number. Other examples are root 3, root 5, root 6, root 7, and so on. So let's look at some of the basic properties of surds. So the square root of a times b is the same as the square root of a times the square root of b. As an example, let's take the square root of 36. We know the square root of 36 is 6, but we also know that 36 is 4 multiplied by 9. So let's take the square root of 4 multiplied by the square root of 9. We know that the square root of 4 is 2. We know that the square root of 9 is 3. And 2 by 3 is also 6. So what we've shown there is the square root of 4 multiplied by 9, which we know is 6, is the same as the square root of 4 multiplied by the square root of 9. Now, a pitfall to avoid at all costs is never say that the square root of a plus b is the same as the square root of a plus the square root of b, because it isn't. Because, let's take an example, let's say the square root of 13. We know that 13 is 4 plus 9, but the square root of 13 is not equal to the square root of 4 plus the square root of 9. The square root of 13 is roughly 3.6. It's an irrational number. It's a non-repeating, non-recurring decimal. So that does continue on. But we do know that the square root of 4 is 2, and we know that the square root of 9 is 3. Now clearly 3.6 is not equal to 2 plus 3. It's not equal to 5. So another basic rule of surds is that the square root of a over b can be broken up into the square root of a over the square root of b. For example, let's take the square root of 36 over 9. That is the same as the square root of 36 over the square root of 9, because think of 36 over 9 first of all. That's the same as 4. 36 over 9 is 4, so that's the same as saying the square root of 4 is equal to, on the right hand side, the square root of 36 is 6, the square root of 9 is 3. On the left hand side, the square root of 4 we know is 2, and we know that 6 divided by 3 is 2. So in this particular example it works out. As it turns out, that is the case for all numbers. The third one here may not even be worth stating as a rule, it's very obvious, but any square root multiplied by itself gives you the number without the square root. So the square root of 2 by the square root of 2 is 2, and so on. Now, in many of the calculations that you'll do throughout this course, it can be useful to break up square roots into a simpler form. So for example, the square root of 45. It can be useful in certain circumstances to break that down. So a technique that you can use is to look at the number 45 and think about the factors of 45. Is there any obvious factor of 45 to which you know the square root? So thinking about that, we know that 45 is 9 times 5. So you could say that's the same as the square root of 9 times 5. But using our first rule of surds, that is the same as the square root of 9 by the square root of 5. The advantage of that is that we know the square root of 9. We know that it's 3. So that's the same as 3 root 5. So there will be instances where being able to do that will be quite useful. As some practice for yourself, you may wish to apply a similar principle to these three here. So what I'll do is I'll put up the answers, so if you want to work on them yourselves, just stop the video for a few seconds and I'll put up the answers in a moment. So this is what you should have got in each case. Root 72 is the same as 6 root 2, root 50 is the same as 5 root 2, and root 8 is the same as 2 root 2. If we take an example of where that might be useful, if you look at some combination of these three, so say root 72 plus root 50 minus root 8, so if we replace root 72 with 6 root 2, we replace root 50 with 5 root 2, and we replace root 8 with 2 root 2. So similar to algebra, if you had 6x plus 5x minus 2x, that would be the same as 9x. In this case, the only difference is instead of x, you've got root 2. So what that gives you is 9 root 2. So that's an example of how you add and subtract surds. You could also have something like this, 3 plus root 2, which is an example of a compound surd. Something useful to be aware of, and we'll use it in a minute, is that 3 minus root 2 is known as the conjugate of that surd. An example of where you might use the idea of the conjugate, and you'll come across this later in complex numbers also, is if you have one compound surd divided by another compound surd. And the way to write that as a single compound surd is to multiply above and below by the conjugate of the denominator. So if you take the denominator here, it's 1 plus root 2. The conjugate of that is 1 minus root 2. So essentially you're changing the sign in front of the square root part. So we multiply above and below by 1 minus root 2. So essentially what we're doing here is we're multiplying by a number over itself. So we are only multiplying by 1, so we're not actually changing the value of this by doing this. So as with all multiplication of fractions, we multiply the top by the top and the bottom by the bottom, remembering that each term in the first bracket must be multiplied by each term in the second bracket. So on the top, if we take 1 by 1, we get 1. 1 by minus root 2 is minus root 2. Minus root 2 by 1 is minus root 2. And then minus root 2 by minus root 2 is plus 2. On the bottom, 1 by 1 is 1. 1 by minus root 2 is minus root 2. Plus root 2 by 1 is plus root 2. And finally, plus root 2 by minus root 2 is minus 2. So you'll see now what the advantage of using this particular technique. On the bottom, you have a minus root 2 and a plus root 2. They disappear, they form 0. So on the bottom, what you're left with is an integer. So you've gotten rid of all surds from the denominator, and that's what this technique does. On the top, what we have is 1 plus 2, first of all, which is 3. And then we have minus root 2 minus root 2. If it was minus x, it would be minus 2x. So minus root 2 minus root 2 is minus 2 root 2. And on the bottom, you've got 1 minus 2, which is minus 1. So we can now divide the top by minus 1. 3 divided by minus 1 is minus 3. And then minus 2 root 2 divided by minus 1 is plus 2 root 2. So what we've done is we've taken two compound surds divided by each other, and we've created one compound surd by multiplying above and below by the conjugate of the denominator. And just one final point on surds. If you have something like a root 2 plus b root 3 equals c root 2 plus d root 3, then whatever is in front of the root 2 on the left must equal whatever is in front of root 2 on the right. So a is equal to c and b is equal to d. If we look at a basic example of where you might use something like this, let's say you had the square root of 8 minus the square root of 32 plus the square root of 200. And let's say you're told that that's equal to some number times root 2. And we need to find out what that number is. Well, if you think about the square root of 8, that's equal to the square root of 2 by 2, because the square root of 8 is the same as the square root of 4 by the square root of 2, which is 2 root 2. So that's 2 root 2 minus. Think of the square root of 32 as the square root of 16 by the square root of 2, which is 4 root 2. And then you've got the square root of 200, which is the square root of 100 by the square root of 2, which is 10 root 2. And that must equal p root 2. So on the left, 2 root 2 minus 4 root 2 plus 10 root 2 is 8 root 2. Again, think of 2x minus 4x plus 10x equals p times root 2, then p must equal 8.